Good afternoon, ladies and gentlemen. My name is Jian Qiangli, and from Shanghai Institute of Architecture, Design and Research. Ms. Patrick just now showed the effects of temperature, climate, and the tropical climate on the building design. Today, I would like to focus on the Supertall building climate response for the hot summer and cold winter climate. So my topic is advanced Supertall building design with the hot summer and cold winter climate. So this presentation includes 5 parts. Introduction shows the background of Supertall building in the hot summer and cold climate region. Second part shows the general design strategy for the climate in this region. And the third part shows the design strategy of the Supertall building. Then it shows the climate adapted design in the 2 Supertall building cases in this region. So now let's start from the introduction. Firstly, I need to define my study scope. The Supertall building is defined as a building which is above 300 meters in height by CTBUH. I have mentioned that this is different from the Chinese code. It is defined as 100 meters above in height. This region, especially the region in China, you can see its location in the map as the south part of China. So the feature of this region is that it has a large area. The population in this region is dense, and its economic is active. So now let's look at the Supertall building in this area. There are 7 Supertall buildings in this region by 2012. This table lists all of them according to the chronological sequence. This first Supertall building is the Jinmao Tower, built in 1998. The tallest building at present is Shanghai World Financial Center, about 492 meters in height. There are some latest completed projects: Nanjing Zifeng Tower, Wenzhou World Trade Center, and the Longxi International Hotel. This table lists the 16 Supertall buildings which will be completed in the next 5 years, including the Shanghai Tower. So from the analysis of the number of Supertall buildings, it can see that the number of Supertall buildings in this region has increased rapidly, from only 1 10 years ago and increased 5 in 10 years, and will be 16 in the next 5 years. So let's look at the facts. This investigation implies that Supertall building is still a new type of building in this region, but its quick spread from metropolis to local cities. The Supertall building will be forming here with the process of urbanization. The basic reason for the true Supertall building is that it can save the land, especially for the metropolis, and it can be efficient and reduce the traffic problems. However, we have to acknowledge that the Supertall buildings are high energy and material consumption, and also a high cost. So it has to face the challenges from sustainability. So the question is rising: how to make Supertall buildings much more sustainable in this region? There's no way to copy. It needs holistic and creative thinking. For me, I believe nature is the best designer. We need to discover and learn from it. So climate-adapted design is a primary approach for sustainable building. It promotes passive design strategy and makes full use of local climate conditions, which in turn improve the built environment quality and reduce energy consumptions. This kind of building design methods has been used for a long time and has been improved by the combination with contemporary technology. And climate adaptive design has been successfully applied in architectural design, such as Kenyang's bioclimate sculptures and for the Swiss RE and so on. So now let's look at the feature of this region climate. The character of the region climate are hot and cold summer and cold winter with damp weather. This region has long hot summers for 4 months a year, and the only 3 so-called stove cities in China are all in this region. In addition, the cold winter lasts for nearly 4 months. It has a lower temperature in winter than any other region at the same latitude in the world. Furthermore, the annual rainfall in this region is larger than 1,000 millimeters. About 60% of rainfall happens in summer. Annual solar radiation is about 115 watts per square meter, and the solar duration is about 2,000 hours. So people in this region have summarized design strategy for the past experiences. It can be seen from the vernacular buildings. For example, the building geometry is compact in order to reduce the shape coefficient. The courtyards are popularly used to adapt solar radiation and improve the indoor environment quality. In addition, natural ventilation is an usual design strategy in this region because adaptive period is much longer. In the modern buildings, high-performance envelope shaping system, green roof, HM, rainwater harvesting system, and solar heating and BIPV are used. However, these design strategies are not always suited for the supertall buildings in the same region. Now let's look at the microclimate around the supertall building. The microclimate around the supertall building is generated by the increase of height, and as atmosphere is inhomogeneous, air temperature, wind speed, humidity, and solar radiation are all in variation along the altitude. The effects of altitude on these parameters are tiny and can be ignored in the low-rise buildings, but they can't be neglected in the supertall buildings. The air temperature has a vertical gradient from warm as the ground to cold in the atmosphere. Its lapse rate is dependent on the ground surface conditions, the transport of heat upwards, and the extension of the air mixing, regardless of the effect of the surrounding area. The standard atmosphere model indicates the lapse rate of about 1 centigrade with each 150 meters of additional height. The air temperature lapse with increasing height indicates that the top of the super building will be 2 degrees lower than the ground level. It can lead to the upper part of the super building at a different climate zone. This temperature difference is helpful to reduce the cooling load, but increasing the heating load. It requires improving the insulation and air tightness of the upper part of the building. Air pressure on building envelope is generated by the different densities of the warm and cold air, which increases with the height between the openings. The pressure gradient of the cold air declines more than that of the warm air with the increase in height, as the density of the former is greater than the latter. The warm air inside flows out at the top of the building, and the cold air into the building from the outside, at a position that is near the building's base. So the air temperature in the large space generated by stack effect can be employed for natural ventilation in the supertall building if the opening can avoid the wind crossing. It can solve the problem of wind-driven ventilation in the supertall buildings. But care should be taken as that too high space can cause uncomfortable air draughts in the space. Wind velocity is affected by the ground surface roughness and typically increase along the vertical. The gradient wind in urban area is reached at about 500 meters. According to typical urban conditions, the wind speed at the top of the supertall building can be more than 2.6 times of the speed at the ground. The average wind speed in the hot summer and cold winter climate range is about 3 meters per second. The average wind speed at the top of the supertall building could be 7.8 meters per second, which causes a serious problem of opening windows and external shading system. And also, the site plan should consider the effect of wind speed accelerated by the supertall building. So on the other hand, the large wind speed at the top of supertall building could harness the wind energy for electricity. The wind turbine has two models to combine with supertall buildings. One is horizontal axis wind turbine, which can collect the maximum amount of wind energy by the variable blunt pitch, and its disadvantage is that it causes noise around the area, especially at night, and sometimes annoying appearance in landscape. The typical building in the structure in London. The other is vertical axis wind turbine, which has a low noise significance and a lower startup speed, about 2.8 meters per second. Its disadvantages are that its efficiency is only half of the horizontal one, and it can't be changed difficultly after the completion. The typical building is Pearl River Tower in Guangzhou. Yeah, in the middle. The amount of harvesting rainwater is dependent on the quantity and the trajectory along the height. The driving rain intensity in light wind is on the roof, where the upper level of the windward facade receives the largest rain intensity in strong wind. So the windward facade can receive more than double the rain intensity than the roof in the high wind speed. The hot summer and cold winter climate region has a large amount of annual rainfall, but is a water deficient area. So the roof area compared to the supertall building facade area is only a small part. It's necessary to harvesting rainwater from supertall building facades. The design strategy for rainwater harvesting need to consider the building orientation and the prevailing wind, the windward facade area of plan, and the building geometry in order to get a large amount of rainwater. And it can also use a rainwater gravity filtration system, which combines the roof and the facade. For solar radiation is affected by the ground surface forms and the lower atmosphere, and increases 4 or 5% with each additional 300 meters of building height under clear sky conditions. In urban areas, the level of solar radiation is reduced as the exposure to solar radiation is influenced by building clustering, density, and the height, leading to the shade and reflection from adjacent buildings. The area of the all tall building above the urban canopy layer can receive more solar radiation than that below the urban canopy. Supertall buildings have large parts above the urban canopy layer, so solar radiation on the building facade is likely to be exposed for a greater period of time than the high-rise building. This provides more potential to harness the solar radiation for solar heating or photovoltaic by optimizing the parameters of building orientation, geometry, building envelope design, and the shading system. After we review the effects of climate and microclimate on the building design, so the case study invested the two new Supertall buildings in this region. One is Zifeng Tower, completed in 2010 in Nanjing, and the other is the Shanghai Tower, which is still under construction. Both of them represent their own city's culture and adapted climate by advanced technology and techniques. So Zifeng Tower, 415 meters in height, is mixed-use super tall buildings, include shopping mall, office, and hotel from bottom to top. The building rises up with diverse tiers, and its standard plan is a triangle shape. So this building applies some passive design strategy responding to microclimate. Its building envelope is designed as a triangle curtain walls. This shape is helpful to reduce solar radiation and has the function of self-shading. As a Supertall building can't mount an external shading system due to safety, the self-shading, low-E glasses, and with the interior shading system, a hybrid strategy for shading in the Supertall buildings, and also suited for this climate region. The vertical facade considers porous steel panel and operable windows. It's much more effective to separate the daylight, natural ventilation, and the shading system in the Supertall building by the different building components. Another case is the Shanghai Tower, known as the tallest green building. Will be completed in 2014. It has 121 stories with 632 meters in height. This building applies various climate-adapted design strategies. It twists the 120-degree geometry is controlled by the three key components: horizontal profile, vertical profile, and the rate of twist. The building geometry dedicated by wind tunnel experiment and the CFD test reduced 32% of wind load compared to the rectangular tower. The building consists of 5 vertical zones. Zone 1 through Zone 8 have 3 atria per floor, which plays the role of a buffer space for thermal comfort. The building envelope adapts the curtain wall system, which consists of 2 glazed walls with a tapering atrium in between. This space can reduce the cooling and heating load. The external curtain wall plays the role as a weather enclosed for the atrium space. Building shading system is accomplished by the different pattern of glass for different building curtain wall. The tower collects the rainwater from the facade and the roof for watering plants. So after the above study on the climate parameters and the design strategies, the relationship between the microclimate and building climate adapted design can be shown in this graph. The first row shows the climate parameters, and the left column shows the building elements, which are affected by the climate parameters. The right shows the response for the left. So compared to the low-rise and high-rise buildings, the Supertall building has its own characters in climate-adapted design. The air temperature gradient and the wind speed increase with the height provide the Supertall building with a unique microclimate. Fully utilization of these features can shape the Supertall building. A Supertall building can use more advanced technology to adapt the climate, which contrives the passive design strategy and the new technologies. For example, the intelligent day lighting control system with double skin facade can conserve energy and optimize task illustration levels. Electrochromic windows can change from clear to optical for reducing glare without losing vision. They are often preferable to mechanical louvers. Supertall buildings apply electrochromic windows can replace the shading system. Supertall buildings have more chance to utilize renewable energy. One resource is from solar energy. Both PV and solar heat are possible to employ in the Supertall building. In addition, the atria double skin facade can be taken as buffer space for passive design. Wind energy is another source for renewable energy in Supertall buildings, and using wind turbine at the top of the Supertall building has the potential for renewable energy. That's all. Thanks for your attention.